Hello, everyone. What I'd like to do here is give a brief overview of some factors that we'd like to consider when thinking about how to structure our data analysis pipelines. So before we begin, we want to think a little bit about how we get to the point where we want to think about data processing and analysis. And of course, where we need to begin is to make sure that we have a clearly defined research question. And so this figure is taken from a great textbook by Portney and Watkins, The Foundations of Clinical Research. And I think it does a really great job of summarizing some of the key steps that one would need to do before going about any sort of data collection. So some of the features or steps included here are, of course, defining your topic of interest, identifying a research problem that you'd like to address, then narrowing down that problem to a specific research question, and identifying many features that you need to answer that question, such as the target population, the rationale for the approach that you've chosen, and then the variables that you'd like to collect. And then at that point, you can then start to clarify your hypotheses and the purpose of your work. And so for this course in Repro Rehab, broadly speaking, the assumption is that you've already done all of these steps. And you're at the point where you have collected data and are now thinking about how best to analyze or process that data. So when we talk about data analysis or data analysis pipelines, it's helpful to have this visual of what steps go into this type of process. So this pipeline is oriented from bottom to top, where we've already discussed some issues with respect to defining research questions. There's a whole area of experimental design that you might want to consider, collecting your data, dealing with raw data, and then doing everything from tidying or cleaning the data, exploratory analysis through statistical modeling and hypothesis testing. So the pipeline is everything from this point of data collection to statistical inference. When we think about reproducibility in the context of science, a lot of the current scrutiny around issues related to reproducibility really focus on issues related to statistical inference. And however, there's much less emphasis or focus placed on the early stages of this process, including the experimental design, and then steps in the data analysis pipeline that ultimately get you to the point where you are testing your hypothesis. So as you've probably already heard by this point, one of the things that you'll want to consider along the way is how best to document and automate this data analysis pipeline to help increase the likelihood that your data, your methods are reproducible. So let's talk a little bit about data here. So when we talk about data, there are a couple of key concepts that we'd like to define at the onset. So the first is this idea of a variable. So when we think about variables in our research, these are measurable characteristics, traits, or quality. And by definition, variables are things that can change from one observation to another. So for instance, if you're in the world of biomechanics, you may measure knee extensor moments during a task like a drop jump. And the moment, the value of that variable might change as a function of time. Alternatively, if you're in neuroimaging, you may measure hemodynamic responses across the brain. And so though that variable varies both with space, so where you are in the brain, and with respect to time. When we make observations, we generally consider these observations to be our data, and the data are the sort of ground truth in the work that we do. So these are what we consider to be our facts. A key point when we think about data is that if we want to characterize some behavior, some process, a single measurement is almost always going to be insufficient to really give us a sense of the underlying process or behavior. So we're often, one of the key things we have to consider with experimental design is how frequently we make these measurements and to have justifications for that frequency. Now, once now we have a sense of what we mean when we talk about data, we also want to take a step back and think about what it is that we may actually want to measure in the context of rehabilitation research. So one feature or one concept that we think that's important in this context is the idea of measuring constructs. So when we think about a construct, this is really a concept that we have that represents something that's not directly observable. And in order to gain some insight into the underlying value of these constructs, we need to measure other observable behaviors that are related to the construct. So what are some examples? So concepts like disability, pain, health, fitness, strength, and intelligence could all be considered constructs that, and the reason for this is that if we were to survey everyone who's sort of listening in on this set of information and to ask each person, how would you measure, for instance, an individual's health? If you ask 10 different people how they would measure health, you might get 10 different answers. And so it's not that any one answer is wrong, but it's that health, much like pain, disability, fitness, and so on, these are constructs that have multiple dimensions. And when we really want to gain insight into the value of these constructs, we often will make multiple measurements. So those of you who are in the world of more often sort of qualitative analysis and development of surveys where you try to gauge people's perception of things like pain, for instance, will be very familiar with this idea that you ask similar related questions in different ways to try to paint a clear picture of the value of these underlying constructs. Now, we may also often measure what we would refer to as physical variables or physical quantities. And so with physical quantities, we have a numerical value and a physical unit of measure. And these units are what characterize or capture the magnitude of the physical quantity of interest. So for instance, we may measure mass in kilograms, temperature in degrees Celsius, length in meters, and time in seconds. Now, some physical quantities we can measure as scalar quantities, where they are a single dimension. So for instance, the measurements that we just described, such as mass, temperature, length, and time. But we may also deal with vector quantities, where more than one number is needed to specify that physical quantity. So for instance, when we talk about a force is considered to be we often capture force in terms of a vector. So it has both a magnitude, a direction, and a sense that tells us in which way the force is increasing in a positive direction. So for any of these physical quantities or constructs or things that we measure, when we capture our variables, we can represent them as either continuous or discrete variables. So a continuous variable is one that can take on an unlimited number of values. But it's important to understand that when we're dealing with continuous variables, let's say we are measuring the marker positions and with our motion capture system, we're going to sample these continuous signals, position as a function of space and time, and the measurements that we make are actually approximations of the true value of this underlying variable. So it's always important to have an understanding of how precise and reliable your measurements are when you are sampling either continuous or discrete variables. Now with discrete variables, these are variables that can only have or can only take on a limited number of values. So things like the number of participants that you've tested, the number of trials in a study, assignment to group, these would all be considered discrete variables. So there's one type of discrete variable which comes up quite a bit, oftentimes in rehabilitation research, and that's the idea of a dichotomous variable, or a measurement that can take on only two values. So when I say that this comes up quite often in rehab research, one way that people use dichotomous variables is by taking the response to a treatment and then classifying or dichotomizing that response into, for instance, those who respond to the treatment and those who don't, so responders versus non-responders. Now, while we don't have time necessarily to go into all the details of sort of statistical analysis and differences between regression versus treating a given variable as being dichotomous, one of the things to keep in mind here is that when we take a continuous variable and we dichotomize it, we often lose important information that can help us understand why we might, for instance, see differences in the response to a treatment among different individuals. So I'm happy to talk about that offline, but this is something just to keep in mind. Is the variable of interest actually discrete, or is this a continuous variable that has been made discrete by perhaps some subjective rationale? Now we can sort of conceptualize different types of data and different types of variables. Again, I want to highlight the idea that when we measure or make these measurements, these data should be collected within the context of a rigorous study design. So I'd like to share this paper. I use this paper in the course that I teach at USC. It's called Experimental Study Design and Grant Writing in 8 Steps and 28 Questions. And one of the really nice things about this paper is it highlights many of the key factors or steps that you really want to think about to make sure that you've developed a rigorously designed study. So just some of these things that you might want to consider that are really important when we think about our data are the psychometric qualities of any assessments that we have. This is often considered with respect to reliability for questionnaires, but you could also think about, as I said before, the accuracy of any other types of measurements that you're using in the context of your study. And then it, of course, includes many different questions related to the experimental design, like identifying the need for a control group and how you might control for different confounding variables that can impair or impede your ability to understand cause and effect relationships. So we won't be talking about experimental design in the context of repro rehab here, but something that I highly recommend people review and take note of early on in the process of designing a new study or experiment. Okay, so now that we have some of the sort of background information out of the way, let's now think about how we might elaborate on the idea of a data analysis pipeline. So on the next slides, what we'll do is walk through some of the key things that you want to consider as you are establishing your analysis pipeline. So broken this down into about 9 steps here. First being making sure you know your data. From there, knowing what you were trying to accomplish. So thinking about the algorithms that you need to employ in order to analyze your data. Once you have an idea of where you're going and what you need to do, you then need to understand how to bring that data into the programming environment of choice. So many of you will be learning one of or two of these 3 languages if you don't already know how to program. From there, once your data are imported into your environment of interest, you then would like to perform some sort of either manual or automated quality control. And you may have things like pre-processing steps that are involved. This could be filtering, averaging, or any number of other steps. From there, you often will take those pre-processed data, compute some summary measures either per individual or across participants. And within these steps, you are often using data visualization to make sure you understand what's happening at each step, but also you use data visualization, the creation of figures to share your results. That's often done in parallel with what we might call your inferential statistics, where you are testing hypotheses. And then finally, you want to do this along the way, but you always want to make sure you save the results of your analysis. So let's walk through each of these steps in a little bit more detail. Okay, so knowing your data, what are some things you want to consider when you are making sure you understand the type of data that you're dealing with in your analysis pipeline? So one of the first things that you want to keep in mind is to make sure that you understand how the data that you're analyzing were collected. So what was the data collection protocol? What kind of hardware were used? Who collected the data? Many of these things are extremely important and can influence ultimately the conclusions that you make. You want to make sure you understand how frequently your data were sampled or your measurements were sampled. So for instance, if you have EMG data, it might be sampled at a rate of 2,000 hertz, so 2,000 samples per second. Or maybe you're looking at data from some wearable sensor that's sampled at a really odd frequency that's particular to that device. Or maybe you're measuring data that, for instance, are in medical records that are sampled at irregular intervals whenever someone comes in to their primary care physician, right? So maybe approximately once per year or something along those lines. So you always want to think about how frequently those data were measured and how that frequency relates to the sort of the dynamics of the underlying measurement signal of interest. From there, whenever we think about data and measurements, we always want to make sure we understand the units of measure. There are often many mistakes that are made in the process of data analysis because of assumptions that one makes when considering the units of different things, right? So as an example, if I want to compute, let's say mechanical power, right, and I want to need the product of force and velocity, generally I want those units often to be in newtons for force and then meters per second for velocity. But if my velocity is in millimeters per second, or I'm dealing with millinewtons, then my ultimate measure of power might not be in the units that I think it is. Again, I'll state this multiple times, but just because you have data or you have measurements, even if they are given to you by some sort of sensor, it doesn't necessarily mean that those measurements are accurate and reliable. So you always want to make sure you have an understanding of each of these sort of psychometric properties of the measurements that you have and that you make yourself. The fifth thing to consider here is the format of your data. So we'll talk a little bit about that. If you're given data, or even if you have your own data, you want to be very considerate about how you organize those data, right? So how are the individual data files named? How are they organized within folders? And then how are subfolders or subdirectories organized within a larger structure? Okay, so let's start with the first topic here. So thinking about how your data were collected. So hopefully you have, for your own studies, a very well-defined data collection protocol. And this would include, every step in the process from how you recruit participants, the instructions you give, the IRB number, the steps in your experiment, and so on. It's often good practice once you write your protocol to have a second person try to execute the protocol by just reading what you've written. And that will help you understand if you have really clear instructions, or if there are, for instance, things that you might do because you know to do them that wouldn't be clear to someone else. And then finally, of course, you want to make sure you keep this protocol in some place that's accessible by yourself and others. So when we talk about understanding your measurements, oftentimes that one of the first things you want to do is to be really thoughtful about the signals that you are recording. So just as an example, we often will record, for instance, let's say we're interested in the neural control of movement. For that reason, we may record EEG, where we have, again, voltage measurements across space and time. So we want to understand how, how those features of our data are organized. Similar, we may do the same, something very similar with fMRI, where we are measuring signals across space and time. And then finally, EMG is also a very common signal that we consider with respect to the neural control of movement. So for each of these measurements, it's important to understand what the underlying sort of physiological basis might be of the signal of interest, and then think about how that information influences the interpretation of what we're recording. Okay. So what I mean by that, we can just take as an example EMG, right? So EMG is loosely related to the amount of force produced by a muscle, but it's not a direct correlation. There's not always a direct correlation between EMG amplitude and force. So you have to be very careful about how we interpret those signals. So if we're interested in things more on the side of biomechanics, we might measure, again, EMG, right? This is the sort of interface with a signal that is the interface between the nervous system and the musculoskeletal system. We may measure interaction forces between our bodies and the environment using force plates and load cells. And finally, we might consider different measures of kinematics using marker-based motion capture, markerless motion capture, or even wearable sensors like IMUs. And finally, a last example of a class of signal that we might be interested in are those associated with physiological systems. So things related to oxygen consumption during exercise, or heart rate EKG information, or even signals associated with body composition. So in all of these cases, and we could even elaborate on this list even more if we'd like, you always want to make sure you understand what the characteristics are of the signal that you're measuring, the device that you're using to measure that signal. So in each of these cases, once you collect your data and save that data in a digital file on your computer, it's going to be stored in some format. And so there are many different types of files and formats that you might use in the context of your data analysis pipeline. So it's also important to understand what you can and can't do with the different file types. So as an example, if I have a file that was saved in MATLAB, so it would be a .mat file here, it may be difficult to open that proprietary file format in another piece of software in I don't know, R or Python. Or maybe if you'd like to open that data in another language, you need to install some plugin or package. So as depending on what type of data you're dealing with, if you are unsure how to bring that data into your programming language of interest, talk to us, and we can often help you figure out a way to do that. All right, so now that you understand your data, the next major step is to make sure you understand what you are trying to do. So what's your goal here? So this again starts as we did at the beginning of this video. Think about what are the questions that you hope to answer with your analysis. Once you are very clear about the question you're trying to answer, I think it's often nice to start by saying, okay, what do I already know? In other words, what's the sort of input to my data analysis pipeline? And then think about how you will know when you've answered your question of interest. So this is often the endpoint or the output of your analysis pipeline. So if these two things are clear, then you're left with essentially the algorithm development. So you want to, if you are uncomfortable maybe doing this sort of on the fly in your head, it's often good practice to write out a step-by-step procedure that is readable by another human that helps you think about what you need to do at every step in the analysis process. Once you have those steps written in a form that's human readable, that seems to be logical, then you can start thinking about how to map those steps to programmable operations, right? So in other words, okay, if I need to do a certain procedure multiple times, do I need to write that as a for loop, or might I need to define a function that does this, that I can call repeatedly? Do I need to use conditional statements, right? Run one set of code if a certain condition is true, and then run another set of code if that condition is not true, for example. So this is a non-exhaustive list, but these are some common operations that you might map on or use as you're defining your procedure for data analysis. So for instance, you might need to define one or more variables from an existing variable, apply a function that is either embedded in your software of interest or something that you create yourself. You might want to extract elements from an existing set of data. So this might be a table, a matrix, or something along those lines. Repeating actions multiple times, as I already said. In some cases, you might want to get user input. For instance, you would like for your user who's running your code to select a file to open that feeds into your data analysis, right? So all of these things are operations that you might want to consider writing in your step-by-step procedure and then mapping to a function or set of code in your language of interest. So another thing that might be helpful for some as you're starting to develop algorithms more often is to write them down in the form of a decision tree, right? So here, this is a way that you can really visualize how data, variables, and information flow through your data analysis pipeline. So these are very helpful for understanding or seeing the outcome of conditional statements and what operations one would perform depending on whether those statements evaluated as true or false. So those are, largely some basics of data in general, and then the two key steps that you'd like to consider when you are defining and developing your data analysis pipeline. Now, for the remaining steps here, instead of illustrating these via text or through slides, what we're going to do is just go through an example in MATLAB that hopefully will help you sort of relate each of these steps to programming or at least commands in MATLAB specifically. And throughout the rest of the course, you'll see a lot of these steps in the language of interest that you choose to learn. All right, so let's now move to MATLAB. Okay, so if I drag this here. Okay, so here we are in MATLAB, and what you're going to see are a couple of things. So for those of you who aren't familiar with MATLAB, this is the primary MATLAB interface. There's what we call a command window where I can type different commands, right? X equals 3. When commands are executed and I, for instance, define a variable, those variables exist in what's called our workspace, which is here to the right. The current folder section here on the left lets me know where I'm, the directory in which I'm sort of living in my computer. And then lastly, I have my editor that you can see here, and this is where I write my code. So for this example, what we're going to do is take some data that I've actually simulated and walk through some key aspects of those remaining steps of our analysis pipeline. So the first thing that we like to do, as I mentioned, is to import the data into MATLAB. So in this case, I have a folder that holds all my data. Within this main folder, I have simulated data for 16 participants, which you can see here. And note that I've given each folder a name that is what we call machine readable, right? So there are no blanks or special characters, and it's ordered. The date is written in a way that's easily sortable, and each participant has the same number of digits for their participant ID number. So within each folder, I have a file, and in this case, I have a CSV file. And if I right-click, open this file outside MATLAB, you can see that, I'll close this, it's just a vector of numbers. In this case, I have hundreds of values here in this CSV file. So now, if I want to import the data into MATLAB, I need to navigate back to the folder where my code is stored. And I can open this file. And what I'm going to do here is just put something called a breakpoint here, such that if I press run, the code will stop executing at that point. Okay, so I'll press run. So the key line of code here is where I call a function known as import data in MATLAB. So that allows me to import my CSV file. There's a bit of code that might be a little confusing, but basically what this is doing is this allows me to automatically update the name of the files so that I can go through and import data for each participant. So now if I was to go back to my main window, I can see now that I have some new variables, participant number, directory, and data that will be updated as I go through my code. So once you start importing the data, the next step is to do some quality control. And I've programmed a sort of simple way to do that. This is just a visual way to specify whether or not I want to keep a set of data. And I'll store a variable known as good data that basically is a 1 or 0, depending on whether or not I think those data are reasonable. So let's see what happens here. I'm just going to continue. Okay. So there's a figure hiding. Let's see if we can find it. Okay, I'll just press yes for now. All right, actually, we're going to cancel this. Cancel. All right, so this is a case where there's a figure that should be, we should see. All right, here we go. So here I have a figure. This would be what we call adaptation data, where people are walking for some number of strides on a treadmill, and our y-axis is a measure of what we call step length asymmetry. So typically I would expect to see these values start from somewhere near -0.1 and start to gradually move towards 0. So this looks like something that might be reasonable. This case where the values just hover around 0, it looks a little bit funny, right? So I'm just going to say no, these data aren't reasonable. Yes for this one, and yes, and so on. So we'll just keep clicking through. So what I'm doing here is using a form of user input that I've, some code that I've written that allows me to determine whether or not we want to keep a certain set of data within our analysis. So this form of decision making is not something I would normally do, which is just a sort of subjective yes or no. you generally would like to have a much more objective reason for including or discarding data through your analysis pipeline. All right, so now we've imported our data. We've done a little bit of quality control and solicited some user input along the way. The next thing we might want to do is to start summarizing data. And so in this analysis pipeline, one of the key things that I will be doing is fitting a model to our data. And in doing so, I'm going to get some output from that fitting process, which are a number of coefficients. So we're just going to run this line of code so I can show you what happens at the end. So I'm going to run change folder to make sure MATLAB can access the data that it needs. Nothing pops up. But the key thing is that I've created a new variable called coefficients_all. And if I go back to MATLAB, type the name of this variable, you can see that what I've done in the analysis process is to compute coefficients, a set of 4 coefficients, so A slow, B slow, A fast, and B fast for 16 participants. And you see that I have NaNs or NaN values that correspond to each participant whose data I said did not look reasonable. Okay? So this is a way that I've used user input to basically discard data that seem to be poor quality. And then in doing so, I've also used that information to make sure that I'm not computing essentially sort of invalid values for those participants. Okay, so now I have a set of summary data for my participants. And if you look back at the last line of code, I make sure to save this variable coefficients all in a file called group data. The last thing that we wanted to do in our list of data analysis steps is to perform some statistical analysis and create figures. So this is an example of a set of code that does just that. We won't walk through all the details here. We'll talk about this more in our MATLAB tutorials. But here I'm going to plot my coefficients. So because I'm dealing with simulations, I actually have the true values of these coefficients that were used to generate the data. And then I also have the estimates that I've made. So I can see if I can validate my estimation procedure. Okay. So I'm just going to run this code, change my folder again. And so now I've created a figure where I can see each panel corresponds to a different coefficient. I've labeled my panels, so I've added some text, right? So this is what you would do if you wanted to make these publication quality. So I have A, B, C, and D. And I've done it in such a way that I can easily compare or see if there are differences between the estimated value of each parameter and the true value that was used to generate the data. Okay? So this would be a case where I can show, like, look, in general, my estimation procedure does a really good job at estimating the true value of each of these parameters. And again, I've now saved not only the data as output, but I've saved each of my figures both in what we call a standard MATLAB format, as well as a PDF. Okay. So if I go to my main window again, I see I have this file called coefficient estimates-group as a PDF. If I right click, open outside MATLAB, I see that it opens as a PDF, and this is something that I could directly submit as a figure for most journals. Okay, so hopefully that gives you a decent overview of what we mean when we talk about data pipelines, some fundamentals of data analysis, and even a few sort of key details related to experimental design. And so, from here, most of you all will sort of move into your different pathways for the respective languages of interest, and you'll get a sense of how to do each of these steps in more detail through some of the remaining discussions and videos. All right, thank you.